Section 7.1, question E11. And one of the mysteries of the formulas for many statistics students is why, when we take a population standard deviation or variance, do we divide by n, and when we take a sample variance or standard deviation, we divide by n minus 1 in the formula. And so this exercise is meant to get at why that is. So we're pretending that we have a population with just 3 units in it. 2, 4, and 8 are the values. And we take a sample of size 2 and replace it, and then take another one, and so on. So we're going to look at all the possible ways we could get these samples, and of course assuming that random sampling would make each of these samples equally likely, we can just take the average then of all the different outputs. So actually filling in the table isn't too bad. That's fairly straightforward. So here the means, of course, are just the adding them up and dividing by 2. The variance, we're given 2 different denominators here for the variance formula. So in order to get 9, for example, we first take 2 minus 5 to give us negative 3 squared is 9. 8 minus 5 gives us 3, and we would square that to get 9, so we'd get a total of 18. And then the question is, do we divide that 18 by 2 or 1? So we're going to try it both ways. This column will divide that 18 by 2. This one divides it by 1, and so on. So you can fill in the rest of the chart using that. Notice real quick here on this 8, 8, or the 4, 4, 2, 2, when both of the elements we sample are the same thing, which is possible because we're replacing the first number before we select again. When that happens, though, we have no variance, right? Or standard deviation for that matter, because everything that we sampled has the same value. So just to point that out real quick. And then taking the average, well, we just add all of these up and divide by the number that there are. Same thing over here. Now we compute the variance of the population using the formula for standard deviation. So this is the original formula that we had looked at back in the early chapters of the book. And if you do that, you will get 6.22. So notice that when we were calculating the sample standard deviation, it was actually when we divided by n minus 1 that gave us the average matching up with the population variance. Whereas when we used that original standard deviation formula that we had learned early on, in other words, we just divide by n, we take the number of data points and divide by n, this gives us a lower estimate of the population variance than what the actual population variance is. Okay, so again, these are based on samples of size 2. This is the actual population variance. In other words, this is the parameter that we're trying to estimate, and these are the estimates that we're getting based on the sample. So the whole point of this is that this dividing by n minus 1, even though it seems strange, gives us an unbiased estimate of the population, whereas dividing by n of a sample standard deviation or sample variance, if we just divide by n like we would do normally for the population, we get an estimate that's too small, and that's what part H gets at then. Okay, and so this is an important thing. You'll notice that in Excel you're given the choice between taking a population standard deviation or a sample standard deviation, and you need to think carefully what the situation is. If you actually have data on the entire population, then it makes sense to take the population standard deviation. If you don't, if you're only taking a sample, like as you typically would in inferential statistics and experiments that you do, for example, then we need to make sure we take the sample standard deviation. If the sample size is relatively small, there's going to be a fairly large difference between the two. What will happen is, as the sample gets larger and larger, the difference between these two will get less and less, so it won't really be as important. But it's still good to understand why there's a difference in the formula between population standard deviation and sample standard deviation.